Slide 1. What is reinforcement learning? Welcome, everyone. Today, we're diving into the fascinating world of reinforcement learning, or RL for short. So what exactly is RL? At its core, RL is a type of machine learning where an agent learns to make decisions by interacting with an environment. Imagine a video game character trying to navigate a maze. The character learns from its actions. Sometimes it wins rewards, like points for collecting coins, and sometimes it faces penalties, like losing a life. The goal here is to maximize the total rewards over time, not just to focus on immediate gains. This is different from our supervised learning. And where the model learns from labeled data, think of it as having a teacher guiding you. In RL, the agent learns from its own experiences, which makes it particularly suited for complex problems where the outcome of actions influences future states. Examples include playing games, controlling robots, or even recommending products online. Slide 2, core concepts and flow. Now let's break down some key concepts in RL. 1. Agent. This is the decision maker, like a robot or a game character. It's the entity that learns and acts. 2. Action. A. This is what the agent decides to do at any moment. For instance, it could be moving forward or turning left. 3. Environment. This is the world the agent interacts with. It responds to the agent's actions and provides feedback. 4. State. S. This represents the current situation of the environment as perceived by the agent. It's like a snapshot of everything the agent needs to know to make a decision. 5. Reward. ER. After the agent takes an action, the environment gives feedback in the form of a reward, which indicates how good or bad that action was. The process is cyclical. The agent observes the state, takes an action, and the environment responds with a new state and a reward. The agent then updates its knowledge based on this feedback and repeats the process. This loop is fundamental to how RL works. Slide 3, Q learning. Now let's talk about a specific method in RL called Q learning. This is a popular algorithm that teaches the agent through trial and error. What's interesting about Q learning is that the agent doesn't need to know the rules of the game beforehand. It explores different actions in various states, receives rewards or penalties, and learns over time. To keep track of what it learns, the agent uses a MAQ table. Think of this table as a map of possible situations, states, and actions. Each entry in the table tells the agent how good a particular action is in a specific situation. There are some important terms here. Learning rate, autonomy. This determines how quickly the agent updates its knowledge. A high learning rate means it quickly adopts new information. Discount factor, Jagrain. This indicates how much the agent values future rewards compared to immediate ones. A higher value means the agent cares more about future rewards. Exploration rate, Ikinaimen. This defines how often the agent tries new actions instead of sticking to known ones. Over time, the Q values improve, guiding the agent toward better decisions and helping it discover an effective strategy to maximize long-term rewards. Slide 4, model-based versus model-free RL. Next, let's differentiate between two approaches in RL, model-based and model-free methods. In model-based RL, the agent learns or uses a model of the environment. This means it understands how states transition based on its actions and can plan ahead by simulating future actions and outcomes. Examples include techniques like dynamic programming and model predictive control. The advantage here is that it's more sample efficient, meaning it can learn from fewer experiences. However, it can be challenging to model complex or unknown environments. On the other hand, model-free RLH does not build or use an explicit model of the environment. Instead, the agent learns directly from trial and error. Examples include Q learning and deep Q networks, DQN. The benefit of this approach is that it can work even when the environment is a black box, meaning the agent has no prior knowledge of how it operates. However, it often requires a lot of data to learn effectively. Slide 5, sparse rewards. One challenge in RL is dealing with sparse rewards. In many tasks, the agent receives feedback only after a long sequence of actions. For instance, in a game, you might only get points after completing a level, not for every single action you take. This leads to the credit assignment problem, where the agent must figure out which past actions led to the eventual reward. To help with this, we can provide intermediate rewards or shaped rewards for partial progress. For example, in a game like Mario, the agent receives positive rewards for defeating enemies or collecting items, but it also faces penalties for inactivity. This encourages the agent to keep moving and taking meaningful actions rather than just standing still. Slide 6, policy and value functions. Now let's discuss two important concepts in RL, policy functions and value functions. Policy function, PP. This defines the agent's behavior, essentially what action to take in each state. It can be deterministic, meaning it always picks the best move, or stochastic, meaning it picks based on probabilities. Think of it as the agent's strategy. Value function, V. This tells the agent how promising each state is for long-term success. It answers the question, if I'm here, how much total reward can I expect? In small problems, we could theoretically compute every possible state in action. However, in realistic systems, the number of possibilities can explode quickly. For example, in chess, there are about 10 models or 80 possible board states. To tackle this complexity, we use learning and approximation methods like neural networks and Monte Carlo sampling. TeachAIr, Slide 7, Core Concept and Flow, Q-Learning. Now let's focus on Q-Learning, a popular method in RL, trial and error. Q-Learning allows the agent to learn without prior knowledge of the environment's rules. It explores different actions and learns from the rewards or penalties it receives. Q-Table. This is a storage structure where the agent keeps track of what it learns. It has rows for possible states and columns for possible actions. The values in the table indicate how good each action is in a given state. Key hyperparameters. Learning rate, A. This determines how quickly the agent updates its knowledge. A high learning rate means the agent learns quickly, but it might forget old information too fast. Discount factor, year rating. This measures how much the agent values future rewards compared to immediate rewards. A high discount factor means the agent cares more about long-term rewards. Exploration rate. This indicates how often the agent tries new actions instead of sticking to known ones. A high exploration rate encourages the agent to discover new strategies. The ultimate goal of Q-Learning is to help the agent discover an effective policy that maximizes long-term rewards.